All right, so let's get started. So there's one heads up. Well, we have no class next week, and then our final will be on December 17th. So after next week, like we have one more lecture before the final. So today we'll keep going on talking about the device and block layers, and then for the next 1 hour, we'll talk about the file system and virtual file system part. So same things. Let me do a quick recall because like we don't have real progress last week. So this should be for the past 2 weeks. So for the NAND flash SSD, or like we say NAND flash, we say like the bit 1 or bit like 1 bit or 2 bits depends on like how many stats they are represented by the electrons inside the floating gap. So for multiple level cells, it is about a cell can represent 2 bits if there are 4 verifiable voltage stats in the cell. So there are 4 stats from 00 to 11, and then which means 4 electrons, 2/3, 1/3, and then no electrons. So this is just a quick comparison. For single level cell, there is 1 bit per cell. So actually it is easier to achieve the verifiable voltage stat. And for the multiple level cell, because we have more stats, or like there are more stats to represent in one cell. So actually you need more time to do both programming and the reading part. So this is just a quick concept figures about what happens inside the floating gap. Like for example, for 00, because there's a lot of electrons, so we call it stat 00. And for this, because there is only like very few, we say like only 1/3 of electrons. So we say this cell is 10. Okay. So if we make an extension to a triple level cell, which means like for each cell, it represents 3 bits. So because there are 3 bits, so we need to have 2 to the 3 voltage levels in one cell. That is at voltage levels. So you can see for the four electrons part, it represents by 000, and then like between 111 and 000, it just depends on how many electrons are there inside. So they're just kind of like 7/8, 6/8, those kind of number of electrons inside the cell. We also talk about like actually because for SSD for NAND flash device, there are several constraints for NAND flash. For example, the read granularity is a patch, but we need to use a block to erase it, and a block is like 512 times larger than a patch. So there is a need for the sequential write access, or like we cannot do in place, we should do the outplace update. So there is a spatial layer called flash transition layer inside the SSD, and the SSD controller will run a flash transition layer. There's another thing is usually most of the device they have is called memory technology device, or the MTD there. Usually MTD there is going to talk to the chips part. So because no matter what kind of device there is chips, if there is a solid state device, there are chips inside. So they need some interface to talk to the chips. For example, to send the read command, and it needs to follow the spec defined by the chip manufacturer. Okay. So the key part is what is inside the FTO. So FTO actually, one of the key goals is to deal with the sequential write constraint. And the reason it needs to deal with it is because SSD doesn't want to let the programmer, or like to let the users to do extra works when they are going to store the data in the SSD. Which means if using this kind of controller running FTO, actually the users do not really know like what kind of constraints the NAND flash chips are usually faced. For example, sequential write constraint, this is the things that NAND flash chips, they are fast. And for example, the limited lifetime. So when you are using the SSD, you don't really know how much of lifetime they are, and then like why when you are going to update the things and how to follow the sequential write constraint. No, because the flash transaction layer will handle all of it for the users. Okay, so how to handle the sequential write constraint? FTO will run a thing called address remapping. From the perspective of user will send the logical block address to the FTO, and FTO will help to remap the LBA to a physical block address. So this process is very similar to the patch table we talked about in our memory management lecture. So this is an example about what happens for this address remapping. Assuming there is a block called NAND flash block 1, and inside the block there are a lot of patches. Okay, so this is the target patch that we are thinking about to modify. Assuming there are already data inside this patch, so the LBA, assuming let's say is 500 and PBA let's say is 800. So PBA just depends on which of the patch it is in the hardware part, because you know there are in the SSD there are several labels. There are channel, die, block, plan, and patches. So there are a lot of labels. So it just depends on, you just think about like for each labels there are several bits to represent which label it is. Okay, and those things combined together, it comes up with PBA. So PBA is a fixed number for each patch. And if we are going to do the update on this patch, it is not allowed to do it in this position. I mean, we cannot just directly modify to, for example, to change this bit to 1 and change this bit to 1 and change this bit to 0. Okay, because there are already data inside. So according to the NAND flash property, you need to first erase all the things so you can write the new data inside. So to deal with this kind of constraint, actually one possible way is you can read out this patch to the DRAM data buffer, and then the controller can modify the things you are going to modify, because inside DRAM actually you can do the in-place update. You can do any update inside DRAM. So after updating to a later state, then the SSD controller will write it back to a new positions, and this is a blank. This is a non-access before patch in another block, for example. At the same time, FTO will remap the relationship between the logical block address and physical block address. Let's say it will update LBA 500 to some other PBA. So if this PBA is 1201, then the mapping will be changed to LBA 500 as mapped to PBA 1201. Actually, the physical block address, this is a fix. So I mean, if this is 1201, then this should be 1200. Then the next one should be 1202, like this. So PBA is fixed. And for the user side, actually, user side will only use LBA 500 to talk to the SSD. So no matter which patches it is changed to in which block, it doesn't really matter, because the SSD controller will help to change the LBA 500 to the correct position of the physical block address inside the NAND flash. Okay, so this is how the sequential write constraint handle. Okay, and then after doing this kind of remapping and then data remodified write moving part, the FTO will mark this prior patch as invalid. And SSD will not erase it, because if SSD is going to erase it, then it needs to erase the whole block. So it is too expensive. So most of the time, SSD controller will only invalidate those updated patches. Okay. So because when time flies, inside each block there might be a lot of this kind of embedded patches, and it will consume a lot of capacity. So let's say if there are too many embedded pages, maybe 10% or 20% of the SSD capacity, it cannot be really used to store the data. And then there comes a thing called garbage collection. So garbage collection is going to reclaim, is going to garbage collecting this embedded page inside the flash block. Okay, but there's still some details for the garbage collection and wheel labeling. We will move this kind of stuff in our next semesters. We have a class called memory and storage systems. So if you are interested in, you can consider to take that course. Okay, then let me skip this part. Another thing to do the record is about interaction with the peripherals, because after finish talking about the hard disk drive and SSD, the next question will be how CPU can access those kind of peripherals. And in modern CPU, there are two ways to access the peripherals. The one is called a port mapping IO. The other is called memory mapping IO. So port mapping IO like this. There are two different address space. One is for memory. The other is for IO device. IO device including hard disk drive, SSD, those kind of things, or your USB. Because they are using a separate address space. So of course, they need to use a separate instruction. So for CPU to access IO address part, you will use the in and out instruction. Compared with memory, when CPU is going to access the memory, as usual, it will use a load and store instruction. I think this one is quite familiar with you guys, because for the traditional CPU, or I think I will put it like this. For the CPU, when it is going to access the memory, it should use the load and store instructions. So when you are using this port mapping IO, the CPU needs to include extra instructions go in and out to access the IO address. And the other, I think this is more commonly used in modern system, is memory mapping IO. Memory mapping IO is IO address and memory address that share the same address space. Okay, so part of the address space will be split and then assigned for the IO device, and the rest of it will for memory address. So because they are sharing the same address space, CPU use the same instructions, the load and store, to access the data on like IO device or memory device. Okay, so this is how CPU interact with different devices. So the decision behind which to should pick, for example, why not pick port mapping IO in current state, is because when you are going to design extra instructions, then your CPU cost will increase. And for ancient time, the reason there is a port mapping IO, this is because for 32-bit systems, the address space, there's only 4 GB to do the addressing. So if your memory is larger than 4 GB, then your addressing will face the challenge. So in that time, it is hard for the address space to separate out a few addressing space for IO device. So what people think about is, let's just separate the address space at that time. But in current CPU now, usually you are using the 64-bit system. So you have 2 to the 64 address space here. And 2 to the 64 means several hundred of terabytes. So you have nearly, it is not possible to use it all of them. In this case, people will merge the IO and memory device. They are using the same address space. They are sharing the same address space, and they can use the same load store instructions. So CPU doesn't really need to design extra instructions. Okay, so this is the reason why currently, in most cases, you only see the memory mapping IO. But I mean, for some embedded device, for some IoT device, if they're not using the 64-bit, and then if they have a very scarce, if they don't have sufficient address space, there is still a chance for them to use this kind of port mapping IO. And because for those kind of IoT device, most of the CPU, they can be customized to support this kind of in and out instruction. Next things, DMA. Actually, DMA is not related to the above port mapping IO or mapping IO. There are two different things. DMA is designed for accelerate the I/O transmission. We know I/O device is super slow. I/O device latency usually is like several hundred of microseconds. Sorry. Oh yeah, so several hundred of microseconds to several thousands of microseconds. So compared with CPU, CPU is in nanoseconds level. So there is a very huge latency gap between CPU and I/O device. So CPU has no that much of resource to wait for the completion of I/O device. And a way to replace the role of CPU is including a new microcontroller. You can think about DMA controller is just a very it's a very tiny, like not powerful CPU. So this kind of DMA controller at its chip, and it usually will only do one thing, as to move the data from I/O device to the memory. And how it works is CPU will set up the DMA controller to say, please tell me to move the address from which durations to which interval of the memory. So you can think about there is, for example, CPU will say first move the first like 4 kilobyte of the data to which starting position of the memory, and this is also 4 kilobyte. And then CPU maybe will set another request is, so please move the last 4 kilobyte of the data in the storage device to which starting point of the memory. So CPU will set up all the things, and then CPU will trigger the DMA to do the moving. So DMA will read out the data one by one, I mean in a byte level, and then to move it to the memory. So because this process, CPU doesn't really need to involve to do anything. So CPU can release to some other task. For example, CPU can do the context switch to do some other progress. Okay, so this is DMA. All right, then that is all for the device part. The next, what we are interested in is we move one step above the block device driver. Device driver is very important, especially for you guys if you are going to join, for example, MediaTek, Realtek, most of the design house. Because in most of the time, what you are going to work with kernel is you need to write a device driver to work with the device and to interact with the kernel. And this is the possible powers that current systems that you will usually use: keyboard, mouse, USB, SATA, PCIe, those kind of device. They're using those kind of. And for those kind of device, actually there are controller on each device. There is keyboard device controller on the keyboard, the mouse device controller, even the controller is very tiny. It's not really powerful, but there's still controller inside each device. Okay, there's also USB device controller on the USB. You can think about no matter what kind of device there is a controller on it. So when you plug in your device on your computer, on your PC, how your CPU can interact with your PC, or how your CPU can run the operating system to control this kind of device. To control this kind of device, inside the kernel, there's using the things called device driver. So actually there is a very deep software stack. I mean, in the kernel IO subsystem, you can think about there is a file system, virtual file system, block device, block layer, and maybe there's patch cache, and there's a lot of different optimization layers. But usually at the bottom, there's a thing called device driver. So each of the device, they have their own device driver. And you can think about in maybe 10 years or maybe 20 years before, when you attach a new device, for example, when you attach a mouse, or when you attach a new CD-ROM to your PC, actually what you need to do is to install a device driver. Because without a device driver, your operating system cannot understand how to control the new device, how to control the new CD-ROM you attach to the PC. So device driver is very important, but maybe you have a question as why now you don't really need to install a device driver. Because now your chipset already includes most of the common device drivers in your kernel. So when you attach the device, you can just use the common device driver provided by, for example, Intel or maybe some other like AMD. But if you are going to unleash the performance, if you are going to do the optimization of a certain device, it is also possible to customize your device driver. Okay, so that is for the device driver. And let us come back to this hardware part. Before talking about device driver, actually, there are two very common types of device for the hardware. One is called a block device, the other is called a character device. And the reason they are going to separate this kind of two different devices is when the kernel is interacting with those devices, they are using a different path. So you can think about for block device, there's a thing called block layer. We will talk about it later. But for character device, actually there is another path, but we will not talk about that path in our lecture. Okay. So block device as example, for example, hard disk drive, SSD, those are block device. And the definition is just right here. Like they're addressable in device specific chunks and blah, blah, blah. So you can think about the thing as block device as you already know the data is there, and then you already know there's a layout for this device. For example, for disk, there are several plates. For SSD, actually there is a SSD layout there. So your data is already there. So you can, for example, you can do the seeking. Seeking is you can get the data from anywhere inside this device. And this is called block device. Like you can get the data from anywhere. You can do the random access on this device. Even for example, for a hard disk drive, you do the random access, it's super slow, but it is still okay to do the random access. I mean, it still supports doing the random access, regardless of how fast or how slow it is. Usually for the block device, people will mount it as a file system because like block actually for user is hard to image what is a block. For example, if you are going to store your movie on a store device, then your movie will be chunked into a lot of blocks. Usually, like each block is like 5 kilobytes. So if you have a gigabyte level movie, then you will get like, not quite sure, maybe several millions of this kind of chunks, several tens of thousands to millions of this kind of chunks. And you need to access each chunk one by one. Usually it is very difficult to access. So if you are going to access this movie as a file label, for example, if you are going to say, hey, I'm going to read a movie from, for example, which time, maybe the first 5 minutes or like the last 5 minutes, they are all file related information. So you need a file system. Okay, so this is about a block device. Oh, sorry. Of course, there should be a fixed number of bytes because you have a fixed amount of the capacity. When you buy a disk, you know your disk is like 12 terabytes or like 2 terabytes. So divide by the number of the block size, you will know like how many blocks there are, and you can know the fixed number of bytes. Okay. On the other hand, the character device, you can think about just like keyboard or like your GPU. Those are character device. So character device providing access to data only as a stream. What do you mean as a stream? It's a stream you can think about. It is not predictable. I mean, the data is not there. For example, for keyboard offering the data as a stream because the CPU, sorry, your PC receive the data from keyboard only when you type the things on keyboard. So they are not predictable, right? So you type the things on keyboard and keyboard will start sending the request to the PC. So this is about the character device, and this is a stream. The stream is a runtime stream. Because this is a stream, so of course you cannot do the seeking. Because before the user type on the keyboard, there's nothing for you to seek, right? And seeking, the definition of seeking is you can get the data from any place of this device. But for keyboard, there is no concept for block. There is only the concept for the keyboard will just keep sending the request for each time when the user type on the keyboard. And also the GPU, because GPU is not a storage device. GPU is for computing. So what GPU will do is GPU will keep sending the, for example, the result to the CPU. So this is a string. And if this is a string, then actually you are not able to chunk into the block, or you are not able to do the seeking part. So this is the reason why for the Linux, they separate those two different devices, and they're using two different, very different IO stacks to handle those stuff. Okay, so that is block device and character device. One interesting for the device driver is actually when you open up your Linux kernel source code, I would say like 70% of the Linux kernel code is device driver, because for each device, it needs a device driver. And maybe for each, for example, for SATA, for PCI, this kind of interconnections, they can also have the device driver to help on it. So this is the Linux kernel 2.6 version, and this is the composition of the like device driver. So you can see for device driver part, they are 50%, 52% for the character device. So character device including TTY is your like user screen, and then video, and then something like all those kind of stuff. So media, GPU, they are all for character device. And then for block device is quite easy, because block device you can think about there's just like disk. It's a SATA disk or it's a SAS disk, the floppy disk, or there is some RAID. So actually there is only 60% for block device. And there is also for networking device. Networking device also need a device driver. For example, your network card. Your network card, when you attach your network card on the PC, you also need a device driver to handle the network card. So there is a 27% for networking part. Okay. So let me give you a quick example about what is a device driver and why it is so important for a device driver. There is a kind of this, I would say like tiny device, and the function is to that the, for example, for the PC or for the notebook, if it is not possible to connect to the Ethernet. So Ethernet actually it is using the L4-3 protocol, right? So for some notebooks, actually, there is only possible to do the to receive the Wi-Fi signal, because there is no this kind of socket to you cannot plug the network cable to the notebook. So if you are going to let those kind of notebooks, they do not have the networking socket, you need to buy this kind of device to extend your notebook by, for example, for use USB to extend to the network socket. And this kind of device, actually, there are a lot of layers inside, because it needs to first have your data to packet by the USB, because this is a USB. So you can imagine if you have a notebook here, you need to send the data to this USB first, and then use to send to the network socket, and then you can send to the internet, for example. So first of all, you need to get a USB to Ethernet control device, because you need to communicate the USB port and the networking port on this device. So the first is about the USB to Ethernet control device. And then on the USB bus, actually, there is a USB bus driver. So this one, if you are going to control this port, then you need this kind of USB bus driver. So the bus driver is going to pack and unpack the USB packet. So for example, if you are going to receive the data from the networking to your notebook, then you need to do the unpack. And if you are going to send the data to the internet, then you need to pack it. Then the second one is about the USB to Ethernet driver. So this is this part. So USB to Ethernet driver is going to export the network interface. Okay, so because we need to follow the interface definition, for example, if this is using the TCP, this kind of stuff, so you need to package your data to follow the TCP/IP protocol, something like that. So actually, you need at least 3 different kind of device driver. So one is about when you insert the whole device to the system, then you need the first device driver. And then to send the data to the USB bus, to send the data on the USB bus, you need another driver here. And then here, when you are going to transform your USB package to the TCP/IP package, you need another driver to help to do this kind of stuff. Okay, so driver is going to do kind of this kind of things. So some technical part, device driver is a program that operates or controls a particular type of device attached to computer. And the good thing for device driver is it can hide the details of how device works. So if you are a user, actually you don't really need to worry about those kind of how this device works and how that device works. Your device driver will handle all this kind of stuff. So you don't really need to know the details about the device. And I think there is another term, it's called firmware, like people will also be familiar with. Firmware means the software program, it runs inside the device. So you can think about FTL is kind of a firmware, just like on your device, there is controller. So what your controller runs is called a firmware. And device driver is going to talk to the firmware. So device driver stays on the kernel, stays on your PC, on your host systems. In Linux, when we are going to interact with this kind of device, there is a thing called a spatial file called device file. So you can, if you have some experience on, for example, to mount the disk or to do something, there's a thing called a /dev/ for example, SDA1, and the /dev is this spatial file. This is /dev is this spatial device file, and this /dev is going to use to interact with the drivers for accessing expansion device. And this is just a very primitive example from the textbook. When you have an applications and you are using the system code like open, read, and write, those kind of system code to talk to the kernel to say, hey, I'm going to read something from, for example, your storage device. And the device spatial file here is /dev/, for example, if your device is on SDA and it is on, for example, SDA1, depends on your partition. So this /dev is that spatial file. And after using this spatial file, actually you can talk to, I mean the kernel, because you are using system code, so the kernel will be activated and then to run a VFS driver, this kind of stuff to interact with the applications. Okay. So once again, kernel modules like device drivers are a piece of code. They can be loaded and unloaded from kernel on demand. So you can think about you have like insmod, insert module, right? So insert module is going to load your module. And then you have remove module. So those is going to like load or unload your kernel modules. And I will do a very brief introduction on device driver. So this is a very typical example for a device driver. Like you are going to print the hello world in your kernel. So first of all, this program can be separated to two parts. The first is about this. Focus on this code, module-init. So module-init, if you have learned the C++, you can think about this is a constructor. So module-init is the things when you insert the module, the first thing that the device driver will run is module-init. So just like a constructor in your C++ code, when you define a new object and when you call the object, the first thing is to do the constructor. So this you can think about as a constructor. So actually, module-init, the input will be a function name. So the function now is called the hello-init. So the hello-init function is this one. So you can change the name if you want, and then what the function is doing also it can be changed. So the format is like it returns, it will be the integer, and the integer means if the return is 0, it means it is successful to call the function, and if it is not 0, then it means it fails. Okay. So the purpose usually is to initialize the hardware and allocate data structures. But now it is super simple because we only run one print k. So print k is a special functions that when you are programming the kernel, you will use is the print function for kernel programming, like the print kernel version. So for print k now, if you run this kind of stuff, actually you can find this stuff in the kernel, the console. Okay. And at the time when you are going to remove the module, the moment when you remove the module, actually this device driver will run module-exit. So exit is going to run, you can think about just like a destructor when you have an object in a C++. So this one, kernel runs a function when the module is removed, and the purpose is to free resource, shut down, and reset the hardware. Okay, so this one, there is no return. It's just a kind of a void because it's just going to clean up all of the things you allocated by this device driver stuff. Oh, and there's a license part. I think it's not super important for this part. And how to build a device driver? Actually, there are two ways. The first is the source tree. Source tree is if you are going to contribute to the Linux kernel, then you can use this source tree. But let's move to an easier part. So you can also build externally, just like most of you are doing now. You build on your own PC and you are not really going to contribute to the Linux source tree. So like you maintain and build the module outside the kernel source tree by like creating a makefile and adding two critical comments. So the first is called this. So your object should be assigned to like your kernel object name. So this is hello-word.o. .o means the object. Okay, so for this line, you will compile the hello-word.c into the hello-word.kernel object files. Okay, and then you will make it. So make is about like this, like you will make it by this command. Okay, so there are two things. The first is go to the directory and read the make file. And the second one is go back to the prior directory and read the make file like this. Okay, so after you do this kind of two, you put these two comments in your make file, actually you should be able to compile your kernel object. And then you can insert your kernel object to the Linux kernel by insmod. And here are some, I would say, like caveat for kernel programming and some knowledge for kernel programming. First of all, is because when you are now doing the kernel programming, which means your CPU is now in the kernel mode, right? Because kernel programming means you are going to run, you are going to program the kernel. You are going to write something related to a kernel. So when the CPU runs the things you are writing, CPU should be in the kernel mode. Okay, because CPU is in the kernel mode, but according to Linux design, actually you are still at the same process, right? You are in some user for example, you are in a user process and you need some kernel service. So the things only change in this is the CPU state. Okay, so when you are in a kernel, when you are writing a device driver, there is also possible to access the information according to current user process. And the thing is, there is a thing called current, in the text structure. So your device driver can find the text structures, and then there is a current stuff inside text structures. And with this current stuff, you can get the information from the current user process. Okay, so here I think you already be super familiar with like your user address space, put your user program and process data, and CPU runs in the user mode. And when there is a system call, CPU will change to the kernel mode and access this kernel module. And this kernel module can be the device driver. So for example, you can also do things like if you are going to get a kernel information, if you are going to get a process information in a kernel mode, actually you can use this current pointer to point to the the common and then the PID part. So like this. So you can have this kind of stuff to interact with your user process. You can get those kind of informations. Okay. And here are also some things that you may know for kernel programming. So kernel, usually you only have a super small stack. So usually there's only 1 to 2 patches. Okay. So the kernel doesn't have too large of stack. So when you are doing the kernel function stuff programming, you should be aware of you don't really do some recursive stuff. Because doing some recursive stuff, then you will consume a lot of stack. Then probably you will get the kernel error. And the second one is when you are doing the kernel programming, actually when you will see some functions at the very beginning, there is a 2 dash line. Okay. So for those function, it means there's low level components. So there's critical components in the kernel. So if it is possible, please don't change those kind of functions beginning with the double dash. And there is one thing about it doesn't really relate to your homework is the floating point part, because for the kernel it doesn't support the it is very expensive to support the floating point operations. Okay, so the reason why it is expensive is it should set the floating point registers while switching from user to kernel mode, and usually it will take hundreds of cycles. So if floating point operations, then you need to interact with this kind of registers, and then you need to wait for a long time. So usually people will not do this kind of floating point operations. And this is also the reason why, if you still remember when we talk about the scheduling part, and the scheduling part when people are talking about the CFS, actually there is a calculation for the you can think about like the priority for each process. Like, so the calculation actually it should involve the floating point at a very original version. But in Linux kernel, they change the way to do the calculation. They do some approximations, so they can skip most of the floating point operations. So you can, if you are interested, you can go back to the CFS part. And I think this maybe at the last few pages we are talking about how to calculate the priority for each process. Okay, so at that part, actually we have to do some approximation on the calculation part. And the reason is doing floating point calculation is quite expensive. Okay, so that is about the device driver. Then we are going to talk about one more layer about the device driver. It's the block I/O layer. So block I/O layer, you can think about as like you have different device, right? Because different drivers is designed for different device. So different device actually you need to control how to put the data on different device. I mean, for example, for hard disk drive, you need to say there is a lot of place and which place you are going to put it on. And then for the SSD, you are going to control which block, which patch the data should be on. So it should be so complex if the user needs to do this kind of decision about where to handle this kind of stuff. So block I/O layer is going to abstract all this kind of stuff. So just like why people using only LBA can interact with this kind of device is because there is a block I/O layer. There is an abstraction layer, so people only use the logical block address to do the interactions, neither using this kind of device related address. Okay, so before talking about the block I/O layer, there are some definitions for the terminology. There's a thing called sector. So sector is the smallest addressable unit for the storage device. Okay, so you can think about sector is like this. So you can think about just like the reason why this term called sector is because hard disk drive is a very representative storage device. So it just directly use a name from the hard disk drive. We call it the sector. Okay, so the sector size is 5 kilobyte, and now it is also possible to set it also to the 4 kilobyte. Okay, and there is the second one is the things that called block. So block is the smallest addressable unit of the file system. So usually the size of the block is larger than the sector. Okay, and because for a file system, actually it usually doesn't know what device you are now using, right? Because for the hard disk drive, SSD, or maybe USB, it doesn't really have that much of information about what kind of device you are now using now. Okay. So it redefines another coordinate called a block. Okay. So block is about like the things on the what file system can see on that storage device. But when your CPU is going to access this kind of data, this block stuff should be moved to the memory, right? Because all the data should be moved to the memory before being accessed. And the same things, those kind of block stuff will be also moved to the memory and becomes a thing called buffer. So buffer is the object which represents a block in memory. Okay, so the storage starts here because you have a buffer in the memory. So you need to manage the memory. So the same things, when in Linux, you are going to manage some things, you need a thing called descriptor. And the buffer, the descriptor for a buffer is called buffer head. So each buffer will have one buffer head to do the management. So what kind of information this descriptor has? For example, the buffer is from which block device and from which specific block. Okay. So this is what buffer head includes. There are all this kind of information. For example, the first one, b-stat, which specifies the state of the buffer. So if this buffer is dirty or locked, dirty means if the buffer is updated or not. So because it is possible for the CPU to write the data to the buffer and the buffer will become dirty. And maybe for the memory part, actually, CPU can lock the buffer. Lock the buffer means it doesn't let the buffer to write back to the storage device. Okay. And the second one is less, b-block device. So it points to the corresponding block device. Okay. So with this block layer, actually, and you can think about for this block layer, there are a lot of devices there. But which device it is? Now, maybe you have 2 disks, you have 3 disks, but which disk that you are talking about? So this should have this like pointer to point to the corresponding block device. And we have the b-patch. So b-patch is, it points to the corresponding patch for storing the block because the buffer is now in the memory, right? So your memory is super huge. Then how to know which patch is like the buffer or the block data is inside? So b-data points to the starting point of the block. So this one is about where is the starting point? Sorry, I think this should be the starting point of the buffer. It will be more precise. Just like where is the locations of the buffer? Because the buffer size could be smaller than a patch. If the buffer size is only 512, which means each patch there are like 8 buffers at most. So where is the buffer in this memory patch? Then you can use this b-data to get the data. And b size indicates the size of the block. Okay. So buffer heads actually is not commonly used now because there are some challenges for buffer heads. The first challenge is buffer head is a large and bulky data structure because a block is smaller than a patch. So just as our example, if the block size is like 512, then for each patch you have like 8 blocks. And then each block, when it is moved to the memory, there is a buffer. So you need to assign a buffer head to it. So it is possible for a patch, you need 8 buffer heads to manage 8 blocks belonging to this patch. Okay. And the thing is, this data structure is not lightweight because given there are all this kind of structure stuff and the size, character, I would say like the unsigned long. So, I mean, you can do some calculation. For example, if all of them, there are 4 bytes, then only the things here, they are already several 10 of bytes for these data structures. And then the thing is, the size of each block is only 512. So if the buffer head is like 50 bytes, which means you are using 10% of the block size to describe a block. So it is very expensive because you need extra capacity to store these kind of buffer head structures in the memory. Okay, and those are just I copied from the Linux kernel. I mean, in the kernel, it is also possible to include more this kind of parameters here. So the blocks, the buffer head can increase to, for example, 100 byte. Then per 100 byte, which means there are 20% extra capacity it is needed to store this kind of buffer head structures. So this is quite expensive. So for the kernel version 2.6, the kernel starts to work directly with patches and address space instead of blocks, because blocks is too tiny. For one patch, it is possible to have 8 blocks or even more blocks, depends on the block size and the patch size. And the second challenge is about the kernel should break up large block I/O operations into multiple needless buffer head structures, because each buffer head it can only represent a block, let's say 512 byte. But if there is a contiguous, like SS is for 4 kilobyte, then for the kernel, it still needs to break this contiguous 4 kilobyte into 8 blocks. So it is not really needed because they are all from the same block I/O operations, but for the buffer heads designs, it needs to do this kind of redundant stuff. So for kernel version 2.5, actually, there is a new flexible and lightweight container for block I/O operation called the BIO. Okay, so I think let's take a 10 and come back later.
没问题。就是这个，他说就是米瑞斯的时候，可是下面是符好像是零的，
对，
就是如果我查一下资料，他这样，他这里写说米瑞斯或是零，然后下面是正压，
哦，我想一下哦，
这是米瑞斯，然后下面是破本。
吧，哦，那有可能是我标错了，因为这个我想一下哦。 这我要查一下，但这个感觉确实是有可能。好，这我再查一下好了。
嗯，好。
Okay, so let's come back. I think there is one. I mean, there are a lot of questions, but I think there is one question I can clarify. The question is about when using DMA to transfer data directly between I/O and between device and memory. How does Linux ensure cache coherence between CPU and DMA engine and blah blah blah? Actually, CPU and DMA engine, there is no cache coherence problem because DMA engine you can think about is a tiny CPU. So it is more like CPU will set up all the stuff for on this DMA engine, and DMA engine will start to move the data. Okay, and these DMA engines will not affect the cache. I mean, when DMA engine is moving the data from the I/O to the memory, actually there is no the cache will not change because the cache is not shared with the DMA. And the rule for DMA is also simple because DMA is just going to move the data from one place to another place. So there is no extra process it needs to run. So it doesn't really have the involvement on the cache part. Okay. So let's move on our main progress first. So we talk about like buffer head, there are two challenges. And in current Linux, actually, BIO used more now. But buffer has, I mean, the design of buffer has is still inside the Linux. Because for Linux, actually, there is a backward compatibility. So which means even now Linux kernel is like 6 point something, it still needs to support those kind of ancient designs, just like the buffer has. Okay. Okay, so BIO part. So for BIO part, this is the block IO operation. It can handle a list of non-contiguous segments. So blocks belonging to an operation need not be contiguous. And this is quite important because you can think about like when you have an IO operations, if you have like non-contiguous part, each can also be represented by one BIO, which means your data structures will be lighter. You don't really need extra data structures there. Okay. So there is another terminology called segment. So segment is a chunk of a buffer that is contiguous in memory. Okay. And this one is a typical figure you can find on a lot of Linux documents or book. So this structure you can think about like this. This one, structure BIO, is for representing one block IO operations. And actually inside these structures, there is a thing called BI-next. This pointer is pointing to the next operation. So because in your Linux, you will receive a lot of operations, a lot of IO operations. So this will chain, I mean, they will chain together. So you can use you can use a BI-next to get the next BIO. Okay. And this is one block here, or one BIO vector represents a segment. So for the definition of segment, these BIO vectors represents a contiguous memory. So you can see like this will link to a patch, and a patch is a contiguous memory. Okay. So for the BI-IO vector, it is the starting of the vector list belonging to the IO operations. And then the BI index means like which the current processing segments it is. So it helps to keep track of the current progress. Okay. And then for patch, you can think about because each patch is like 4 kilobytes, and it is also possible to be larger if you use a huge patch. Okay. So on each patch, actually you can think about there is maybe any place there can be a segment. So if one of the BIO vector is going to read out this segment. So there are several things in this. The first is about the patch number, offset, and then the patch number for this BIO vector will point to the starting point of this patch. Okay. And then the offset means where is the starting point of the segment, because the segment might not be at the very beginning of the patch. It can be anywhere inside this patch frame. Okay. So here it comes an offset. And then there's a length. Length means what is the size for the segment? The size can be large, can be small, because I mean, the BIO, the goal for the BIO is going to offer a very flexible structures for accessing the IO with represented by only one data structures. So the segment size doesn't really need to be a buffer. For example, like in the buffer head, I mean, the segment should be a block, but now it can be smaller than, or you can be larger than, it just depends. Okay, so this is just a quick overview for the block IO there. Okay, and we're finished for the block IO there. So let me move on. One moment. Let me move on to our next topic. So file system and virtual file systems. Like we finished device, block device driver, and block IO layers. And file system actually is a quite complex topics because there are a lot of, I mean, there are a lot of data structures to talk about the file systems and also the virtual file systems, and also what is the positions between the virtual file system and file system. Okay. So for the file systems, you already know those kind of stuff. For example, when you are using the Windows, like there's NTFS. So when you are using Linux, maybe you will be familiar with the ext4, and maybe there are XFS, and there is also some other kind of file systems. Okay. And maybe there are ZFS. So actually there are, so for example, when you are using the Android phone, the file system will be F2FS. So actually there are a lot of different file systems. And also in a same PC, you can have different file systems. For example, for this disk, you are going to use, for example, ext4. For another disk, you can use for maybe ZFS or XFS. Okay, and even for the same disk, you can also partition the disk with using different file system. So it is very flexible for like different combination with the file system and the partition. Okay. So above the file system, there is a patch cache. So patch cache is when you read out a file once, you don't want to read out the file second time or the third time because reading a file, it takes time. So if there is a sufficient room in the memory, then you can put your file in the memory, and that part is called the patch cache. And then when this file system is going to talk to the users, actually they're using the things called virtual file system. So the reason is if now when the user program is going to talk to different file system, for example, for one disk you are using two file systems, ext4 and XFS. And because ext4 and XFS, they have different protocol. So you are using different, for example, when you are going to read a file from ext4, for example, you are going to create a file or do some things, maybe you have some amount of parameters, but those parameters are different from XFS. So if you are a user, you are going to send the comment, then you need to customize your comment. Then this process will be quite complex and tedious. So a better way is there is a way the system can automatically translate those kind of stuff for you. And this is the virtual file system. With using the virtual file systems, like you have a uniform protocol. So you can use a read, you can use a write, and then for this read and write, the virtual file system will do the redirect to different file systems near the block IO layer. So the virtual file system will help you to translate those kind of stuff to a correct versions to talk to different file systems. Okay, so for a user, actually, you only need to know, oh, actually, this disk is for ext4, and that is for XFS, or that is for ZFS. But actually, different file systems, their protocol is different, and then their operation, their implementation, they are all different. But for the user, we don't really need to know about what those differences are. And we only need to talk to the virtual file system using the same comment, using the same way. So the virtual file system will help to translate all those kind of stuff. All right. So file system, the definition is a method and data structure that the operating system use to control how data is stored and retrieved. Okay. So without the file system, data will be one large body on storage media, and it is hard to separate and identify. As our prior example, if you're movie file is like several gigabytes there. Then if there is no file system, then you can think about there's just like 10 of thousands or 100 of thousands or even millions of data blocks that you can access. But actually data blocks, you don't really know what is the beginning of the movie. And if you are going to get from the middle part of the movie, if you are going to start from like the first, maybe, I'm not quite sure, maybe the first 1 hour, and it is not possible because the block layer, the data block, doesn't really contain any user-related information. Data blocks only talk to the lower level. I mean the device level stuff. So if you are going to know, okay, so this is a movie and how long it is, and then what type of movie it is, those kind of stuff, and maybe what type of music it is, then you should have this kind of file information. And those kind of file information, those kind of data structures, they need to be maintained by the file system. Okay, and because like for different file systems, they will have different way to talk to the device, and there are different ways to handle how to partition those kind of device stuff, and then how to define different directory, how to define different files, and how to do the parallelism. So blah, blah, there are a lot of stuff they can tune. So there are different file systems. Okay, and also there is also the classification. For example, for disk-based file system. So disk-based is for like hard disk drive or SSD. Then you can have ext34, XFS, EXFAT. And then for networking file systems, it is about not only the disk, but you also need to think about the networking part. So there is also the network file system stuff. And okay, but because there are a lot of stuff, right? There are device block, device driver block, IO layer, and file system. So I try to use some very common example to that you have a feeling about what is the rule for those kind of stuff. So I try to analog the IO system to a library systems. So if an applications is just like a library users, okay? So a library user just like a very like typical users like you when you are going to access the book in the library, then you are a library user. So the application usually needs to get the file. So it's just like we library users need to request books. I mean, there are different there are different books. So how to get those books in the large library, okay? And when the first step, like you are a library users and you will go to the counter and then to ask about, so can I get a book? And the counter will use a catalog system to find, okay, so where the book is. So the catalog system is just like file systems. So it organizes all the books to that oh, actually it is what is the positions of the books, or what is the position of the files. So the catalog system will help you to locate the book. Okay. And then the library staff, you can think about it's just like a block there. So the library staff will physically get the book from the correct shelf and slot. Okay. So the block there will get the data from a certain device according to the information from the file system. So the file system will only get a block IO layer about, oh, actually, maybe it is on which disk and then what is the LB it is. And the block there will get this request and then capture like as like the BIO, and the BIO will send to the driver part, so you can get out the file. And the shelf and slots is just like the device. So each device just like a different bookshelves. But bookshelves actually you can, for example, for one bookshelf it is possible like it only stores a very thick book, and for some other bookshelves it is possible to store very thin books. So bookshelf there is also there is also some room for customize. So it's just like different device. Okay, so the block layer or the library staff will go to the correct bookshelves and then get the correct book for the library users, just like your block layer will get a correct data for the applications. So I think this is a very life related examples to analog the IO system to the library. Okay. So because this is called a file system, so first of all, let's first start from the file and directories. And I think this both are quite familiar from the user because users only know files and directories usually. So file is a linear array of bytes that can be read and write. Okay. So each file has a low-level name. I mean, file name is not the low-level name. The file name is called a high-level name. Okay, because actually, excluding the file system, actually for your block there, your device driver, they really don't know what is the name for the file. So the file name there's only inside the file systems. Okay, and the low-level name is a thing called the inode number. So inode number is more like the ID, the represented ID for each file. So just like you all have the ID number, and the ID number is unique in the world. So just like the data, the file data has also their inode number, and this inode number make them unique on the store device. So on the same store device, different files will have different inode number. They will not share the inode number. Okay. But it's not the case for the file name because file name is an abstract thing. There is some possibility you have the same file name, but you are talking about different files. Because when on the same disk, you have different like file systems, then it is possible the two file systems give you the same file name, but those data they are storing on different location. Okay. And but the thing is, usually we users do not really know what is the inode number for each file because we users only know the file name part. So actually there is a need for a data structure to connect the high-level file name to the low-level inode number stuff. So this is the reason why file system is quite complex because there is a lot of this kind of data structures to bridge like the user, also like informations and the storage level informations. Okay, so a directory is just a special type of file with specific contents in Linux. Okay, so actually you can think about like directory is just like a file. So there is not really the directory stuff inside the Linux. And each directory is each directory also has their own inode number as well. Okay, because this is a file, so each file has their own inode number. So each directory also has a inode number. And in Linux, it uses the directory tree. So the leaf node means the file. And the non-leaf node, just like between the root and the leaf node, there is directory. And the root means the root directory. Okay. So the slash is the root directory. So when you are using a Linux, you say you are going to change the directory, you use a cd command, you will start from a slash, is because this is the root directory. Okay. So the slash can also be a separator to name subsequent files. Okay. So a file, there's typo. A file referred by the absolute path name from root. So when you are going to get the absolute file path, then it should always be start from root. And then if you are not going to get the absolute file path name, okay, so because there's also a relative path name, you can also get from like /temp and then /hi.txt. It is also possible, but this is not an absolute path name. Okay, so and because the directories and files, actually there are different category stuff. I mean, in the file system, there's a way to differentiate. Oh, this is a directory and that is a file. So actually, the directories and files they can be using the same name, but the file system can differentiate from it. So this is the reason why file name is not important in Linux, because for we human beings, like we use the file name to differentiate. Oh, this is the directory and this is a file, for example. But for the Linux, actually, file name is not important because people are using, Linux is using the inode number to identify the files and directory, those kind of stuff. So in Linux, there is no difference between file and directories. I mean, the different stuff is about the data structure part. I mean, in the data structure, I mean, there is a way to identify this is a file or this is a directory. And Linux doesn't care about the file extension. So file extension is just like .sh, .txt, .docx, .pptx. So those are all the file extensions. But Linux doesn't care about those kind of stuff. I mean, it is also possible you just remove this kind of blah 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 stuff. You are also possible to open it because there is, I mean, even in the Linux, there is a way to set up what kind of application you are going to open the file. Okay, so file extension is not important in Linux. So let's go a little bit deeper into some technical stuff. Okay. So there is a terminology called file descriptor. File descriptor is an integer to identify the open file in all file-related operations. So what is called open file? So who opens the file? And open file is a process opens a file. Okay, because in Linux, actually, it cares more about, I mean, which process does what kind of stuff. So in Linux, users also like it's not that important. It's not the main character. The main character is a process. So a process opens the file, then that file will become open file. So what do I mean like the process opens a file? Because all the files, they are stored on a storage device. So in most cases, those files are not open. They are only on the storage device. But even in this case, each file has their own inode number. Even the file is not open, but we still need a way to identify different files on a storage device. Even they are not open. So inode number is for that case. But when there is a process, it opens the specific files. Then that file will get a descriptor called file descriptor. Okay. So the file descriptor assigned by the kernel when a file is open and is valid only within a process. Okay. So two processes may use the same file descriptor because we say the file descriptor is only valid within a process. So different processes, they have their own file descriptor. So even like the two processes using the same file descriptor, they are not saying about the same. They are not representing the same file. Okay. So you can think about like this. So process A and process B, their file descriptor table will always start from 0. And maybe there are 20 or maybe 30, 40 file descriptors, depends on how many files are opened by this process. Okay, so the FD2 for process A and FD2 for process B, there is no relationship between each other. I mean, they may be the same file or may not be the same file. So it doesn't really, there's independent. Okay, so file descriptor only for each process. There's no crossing process stuff. Okay, so inode, which means the files or directory has just one inode, and it contains the metadata such as the access rights, data, pointers to the file data, blah, blah, blah. So you can think about inode is going to describe the information for the files or directory on the disk. Okay, so this one is, you can think about, though it maintains all the information for each file or directory on the disk. And file descriptor is for the process. Okay. So actually for the file systems, for the process, if we are going to get, for example, where is the like inode stuff, then there is also two more tables here. One is called the open file table, and the other is called the inode table. So the open file table is going to be stand in the middle between the file descriptor table and the inode table. And inode table is just about like how to get the data on this, those kind of stuff, low level stuff. But open file table is about, because in Linux, for process level, there is possibility like two processes will share the same file descriptor as when the process do the fork, right? When the process does the fork and there is a child process comes, then at the moment they do the forks, two process will share the same file descriptor. I mean, they will first share the file descriptor table. Okay, so there is a case like this. So we need the open file table. Let me give you some more example about why we need another table stands between this kind of file descriptor and the inode table. Okay. So the goal for this kind of open file table is to relax the complexity of the inode table. So first of all, if we have two processes, process A and process B, and then open the same file. So for this case is fd0 in A, and then fd3 in B. Okay. Even they are not the same file descriptor, but you can see in the open file table, it indicates but fd0 in process A and fd3 in process B, they finally point to the same inode number. So when they point to the same final inode number, it means they are going to access the same file, because inode number means the ID for each file on the disk. So if the inode number is the same, it means the data is the same. Okay. So then why we have this kind of design is even they are going to access the same file, but they can have different behavior. For example, for process A and process B, they can have their own access mode. For example, for process A, maybe the privilege for process A to the file, I mean the file number 1976, maybe it's read only. And for process B, maybe it is maybe write only. So for read only and write only, actually it is controlled by this open file table. I mean, there is a privilege, there's an access mode in this open file table to indicate this is like read only, write only, or read write only, or like executable, those kind of stuff. And then they can have their own individual file offset. What do I mean for the individual file offset? So for fd0 now for process A, even they are going to access the same 1976 file number. But if the file is, I mean, it's large, for example, it's like 1 gigabyte. And then for fd0, it is possible to access from the very beginning. And then the fd3, maybe it is possible to access from the tail of the file. So the open file table offers this kind of flexibility for people to access it. And they also share the reference count, and then you use file descriptor to get a log. Okay, so those kind of stuff, actually, they can be maintained in the open file table. Okay. And there comes another case is process B inherits files from process A. So maybe process A do the forks, and the children is process B. And sorry, the child is process B. So in this case, just like FD2. Okay, so FD2 and FD2 here, they share the same open file table. Okay, so you can think about like process A forks process B, right? And they just do the copy for the page table, and then they share the same open file table, and then they share the same like inode. Okay, so once process B maybe do some update on a file, then they can do a copy on write, then they will point to some other place. So with this open file table helps, they can reduce this kind of design overhead. And maybe you can say, yeah, it is also possible. You don't really need an open file table, but then you will have very complex logistics behind the design of the file descriptor table and the inode table, because you also need to consider about like the process operations and the file system information there. Okay, so this is like 3 different tables in the file system. All right. So there are also some like interesting things for the file system. There's a thing called soft link and hard links. The reason I point out the soft link and hard links is because you also use this kind of stuff. Like when you are using the Windows, when you are using Linux, maybe you will make a shortcut on your desktop, right? So shortcut is soft links. So shortcut is just like in Chinese, it's like 捷径, like this. And shortcut is a separate file contains the path or reference to the target file or directly. So we can take a look at the example here. Okay. So if here is a file.txt and you make a shortcut, so you just in your Windows or Linux, you can just make a shortcut by you right click your mouse, and then there is a menu, and you can click you are going to make a shortcut, and then there is a thing called like file.txt, the shortcut file. Okay, so actually shortcut is they have their own inode numbers. Okay, so they have their own like file.txt, there's an inode, and then this is only another inode. But actually, at the background, they are sharing the same content. So how does it happen? Because the second inode here, it points, it's just like a loop. You will point to this one, and you will go back to here. So like this, and you will come back to here, and then you can access this kind of stuff. So this is about the shortcut. So what does it mean? Like it needs to indirect to get the real file is if you first make the shortcut and then you delete your original file, right? Then your shortcut will become invalid. Okay. So this is the things like why when you delete your original file, your shortcut will not be valid. It's because when you delete your original files, then your shortcut cannot find where is the original file is. But it is possible for you to directly design a shortcut. It doesn't really matter because this is only the shortcut. Okay. So there are soft links, and then there is a thing called hard links. But hard links, in most cases, you will not really use in most cases because hard links usually use on crossing the file system part. So hard links is the file shares all the attributes of the original file, even the inode number. Okay, so it uses a counter to monitor the number of links. So for example, if for file.txt you are going to create a hard link now, then these two files, they share the same inode index. So also they share the same, the data inside the physical disk. Okay, so because you are doing a hard link, so there is a counter here to represent how many hard links there are. Okay, so even now, no matter you delete the file.txt or the hard link part, for the another will still becomes valid because the counter will decrease and the file will only be deleted only when the counter comes to 0. So if there still has, some other files using the hard link to access the data, then the data will not be deleted. Okay, so this is quite different from soft links. Because for soft link, if you're going to delete your original file, then your shortcut file cannot get the data. But for hard link, no matter which one you do the deletions, the other ones still can access the data. So only when all the hard links are removed, then they will be removed. Okay. Okay, so let's move on for the layout concept for. Yeah.
The only case I'm using there's two requirements.
Yeah.
Okay, so
Okay. So the layout concepts for the file system on storage device. Okay. So an overview of key data structure used by file systems. The reason I just highlight on the storage device is for next week, in 2 weeks later, when we are talking about the virtual file systems, then we are talking about the file system in the memory. Okay, in the memory, it's not really about talking about like we store data in the memory. In memory, it's talking about the data structure part. Because for the file system and virtual file system, what we talk more about is about the data structure, how to represent the data on the storage device. So there's two different positions for the data structure. One is on the storage device. The other is in the memory. Okay, but those are all data structures describing the data on the storage device. So for the file system, we don't really talk more about the content part. Okay, so content part is like your file. You store your file on the storage device, right? But because there's a file system, so you also need a lot of metadata, a lot of data structure to describe the file you store on the storage device. And the data structure and metadata, they can be on the storage device, and they can also be on the memory device. Okay. So this is the typical stuff for a file system. Like there is a directory tree. There comes a subdirectory 0, and there is 2 files, and there is a subdirectory 1 for another directory, and there is a file 3 inside. And for the root, actually there is a thing called file 0. And when you transform it to the file system, then you will see this kind of a structure. So there are different kind of like data structure, like inode, those kind of stuff. Okay, but I will use this example to make it clear. So for each of the file system, it always starts from the boot block and a super block. So the boot block is if this device is going to use as a boot device, then there is a boot block for the store device. Because once the computer boots, actually there is nothing, there's no anything in the memory. Also, there is nothing in the cache. The only data there is on the store device. So most of the kernel data structures and then your kind of information, those kind of metadata, they are all stored on the store device. And you need some way to activate those kind of data structure and to move them into the memory. To move those kind of kernel data structure into the kernel space in the memory, you need to move your, not quite sure, your user information in the memory. So this boot block is going to do this kind of stuff, okay? And follow up to the boot block is a super block. So super block is, you can think about super block is going to describe different file system. So each super block is going to describe its own file system. When you do the file system mounted part, then for your ext4 file system, you have the ext4 super block. When you are using the XFS file system, you have an XFS super block. So super block is going to describe the properties of the file systems. So you can also think about super block is going to control those kind of stuff you can do on the file systems. Okay. And then it follows up will be the inode table, because without using the inode table, you cannot get the data. The inode is going to breach the real data and the inode number. So you need some way to get this translation. And follow up, it is the root directory and then files content in data block. So actually you can think about this super block and inode table, they are all also like metadata part. And then the real data, they are stored in this kind of stuff. We usually call them data blocks. So there are two different kind of data blocks. One is for the file content, the other is for directory. So some other will also call the for directory part of the directory block. Okay. Okay. So your data content will be stored in this, for example, file one's content in data block, just like this. So your file one will be stored here. But the thing is, but how do you know how to get a data? What is the positions for files one? So you may need this kind of inode table to redirect your request, redirect your kernel to guide your kernel to know, oh, actually your file is stored in this directions. Okay. Sorry. Okay. So there is also a thing called the directory block, just like the data block, but it is used for storing the directory stuff, because this one is the subdirectory. So for each directory, you will be represented by the directory block. So inside directory blocks, actually there is a thing called directory entries. And these entries, they will store some stuff. For example, for the mapping between the file name and an inode. So because we need to know what is the data stored in the store device, what inode number it is. And we also need to know what is the file name. So the link between the file name and the inode is stored in the directory block. Okay. So here, like file one's file name, then you can say, hey, actually, this is stored on the inode 4. And file two's file name, you can know, hey, actually, it is on the inode 5 place. And with this inode 4 and inode 5, go back to the inode table, you can also know, oh, actually, where is the location for inode 4 and inode 5. The inode table will guide the file system request to the correct position. Okay, so this is just a concept. So let me give you a concrete example about a very also like typical file system called log structure file system. Log structure file system is a quite simple one, because if we are talking about like ext family or like some other like modern file system, a little bit complex, because they are having a lot of optimization and function supports. So I just use a very primitive one. Okay, so the reason why we need low-order file system is the sequential access issues. Okay, so if you still remember when we are talking about the hard disk drive, for hard disk drive actually, because the plate rotates all the time, so a good access behavior is do the sequential access, just like we access the data and then behind the data. So if the order is aligned with the rotation order, then you can get the data very smooth, fast. But if you are going to get the data across the whole disk plates, then you need to take a lot of time because you need to seek the data, you need to wait for the rotating. So low order file system is designed at a time when people are using the hard disk drive. Okay. So sequential access, like maybe you will think about writing data in sequential order is enough, right? Maybe you're thinking about maybe what we are going to do is to write the whole file to pass it to the Linux because we pass it together, so probably they will be stored in the sequential order, right? But the thing is not like this because there is a write buffer. So given an example like this, so there is a write buffer. So you, for example, your data code data D, and data D there are 4 blocks, like DJ0 to DJ3, and then you will have an inode J. Inode is going to describe this file D. So inode will include 4 blocks because you have 4 pieces. So block 0 means like A0 and block 1 means A1, the address 1, address 2, address 3. And then here is DK. So this is called the segment, okay, for example. So what we are going to do is like this. We are going to write those kind of data on hard disk drive, right? So now we can say they are sequential because they are all on this kind of stuff together, okay? But the thing is, if there is no write buffer, like if you send the comments, you send a sequential order comment to the systems, their possibility is when you are going to write the data on the hard disk drive, maybe you write the first data, and then the file system maybe is interrupted by some other kernel functions. Then your disk will still keep rotating, but because you always go to run other stuff, so you will not really write the second one in the neighbor. Okay, so actually, without this kind of write buffer design, there is some possibility is even you send the data in a sequential order, but because there are some interrupts, there are some other stuff happens, or maybe there are multiple processes. So your data will not really be stored on the hard disk drive in a contiguous manner because the disk rotates all the time. So even there is a little bit delay, your data. So with this write buffer, like the system can pack those kind of data together, including their data structure together, and then they can write to the hard disk drive. So here comes another example. Another example is actually this segment, like we write this all stuff together, including the data and the metadata part, right? D means the data, or the file data, and the inode means the metadata. So there is a possibility is, like if there is no write buffer, even you write those data to the hard disk drive, but because you still need to wait for the file system to maintain this kind of inode stuff and then to write to the hard disk drive. So it is possible this D part and inode part, they are not together. They are separated on the hard disk drive because we still need, the kernel still needs some time to maintain this inode stuff. So there should not be, I would say like instantly finished. We still need some time. And the time when the file system is preparing the inode, the disk already rotates several times. So you already don't know where should you write the inode near the data. Okay, so contiguous, if we are going to make it contiguous, then we need some place to buffer all those kind of data and metadata together before writing them into the disk. Okay. So this is about tricky stuff for the sequential access stuff. Okay. Okay, so this is called sequential. Like for the hard disk drive, when the system directly read out this stuff together, right? Because your disk will rotate and your disk head will start to read out 1, 2, 3, 4, 5, 6, 7, and read out those kind of data into the memory, and CPU will start to parse this kind of data. So CPU will start to parse, and CPU will know, oh, actually your inode is here. So with using this kind of inode, CPU can know actually where is what is the direct what is this DJ0 means. Because for CPU, actually CPU only know, oh, actually this is the address, and those are all 0 and 1 there. Okay, so with all these data structures, it is hard for CPU to parse, oh, okay, this is for the first block, second block, third block, and fourth block. Okay, so CPU with accessing the whole, the segments, and CPU can parse out, oh, actually there are two different IO operations, and the first one, it starts from A0 to A4 is for the first inode, it's for the first file, and so the second inode is inode K, the second file, then it is for the DK part. Okay, so this is the how contiguous work. Okay, so this is an example. We need an inode to find out the data, because inode map the data block and then the address on the storage device, right? But how could we find the inode, right? Because this is the reason. This example is just about because we can see this is an inode, so we know, oh, this here is an inode, so we can get it. But how can we get an inode part? So here comes an old Unix file system. So it organized in an array and placed on disk at the fixed locations. So from A1 to AJ, you can think about for AI to A star, you can think about those are all data part. So for old Unix file system, they separate the data and the metadata. And this one is where the inode stored. So inode 1, inode 2, inode 3 to inode n, they just put at a very rear of the disk. So of course they will have some, reserve space. So if you have more extra inode, then you can just append after inode n. It is also possible to do this. And with this kind of structures, actually, if we are going to get the first data or the second data, we just start from A star and we can get the first inode and second inode. So even you are going to get maybe the 900 data, you just go to find where is the inode 900. Okay, so and the inode size is the same. So inode size, you can just say the starting point plus 900 times the inode size. So you can get to the starting point for the inode 900. And getting this inode 900, you can get the data. So this is the old Unix file system it does. Okay, like this. A inode equals to the start path, blah, blah, blah. But here comes the problem. Because the inodes are now separated from the disk. So this is not the contiguous. Because if your disk needs to get the data from inode part and then get the data from data part, then the problem will be you will be at least 2 disk access, right? Your disk should rotate 2 times. The one is to get an inode, and the second one is to get the correct data. So it takes extra time. Okay, so the thing is about if it is possible to minimize this kind of disk access, and this is what log structure file system is going to do. Okay, so I think let's stop here and then let's come back maybe in 2 weeks. Thank you guys.
像刚刚提到这个 soft link，其实也是举例，就是我们在桌面创造一个档案捷径。
对，
那 hard link 如果在 user 的角度的话，它大概会是怎样情境？
它那个比较少在 user 就是 UI 界面出现，它比较少出现在你在有 server 的时候，你有2个档案系统，然后你想要复制，你想要做档案的 backup，
哦
你想要从一个档案系统 backup 到另外档案系统的时候，你就用 hard link。对，所以我没记错的话，Linux 应该没有提供 GUI 是可以让你直接做 hard link，但是它的就是你可以直接在它的旁边那里面直接输 ln-h 吧，就是 hard link，ln-s 就是 soft link，就它有一个 link 的那个 function。对对对对，是。
对，这个是干嘛？因为它不是可以，它不是这里就是1对1，就是
不一定哦，1对1没错，档案是1对1，可是权限不是1对1。就你今天同一个档案好了，你不同 process，你可能一个 process 说它只能读，另外 process 说它只能写。那这个读跟写这件事情的控制是透过中间这个来做控制。所以你这个 open file table 里面，其实它还会有一个单位是你的顺序权限是什么？
对，它也是有可能会就是多个，然后只下一个，然后一个是说它有什么权限，另一个是一个权限，这样子。
就是它其实就是它有点像这样子，就是它是不同的 process，但它指向同样一个档案，1976是一个档案。
哦，
那这2个 process 呢，虽然都是存取同一个档案，但是它们的权限是不一样的。
哦，
它们的 access mode 可能不一样，一个 process 可能他说它只能 read，另外 process 可能是可以 read 加 write 这种的。对，
哦，
对，就是它还有很多别的啊，就是例如我举例来说好了，有这个 table 好处就是，你今天如果想要举例来说，你可能读的位置也可以不一样，因为不然你这个档案那么大，你这个档案可能1G，那你今天 process A 可能想要从第500个 megabyte 开始读，那你这个 process B 可能想从头开始读啊，
哦，
那它就会把它放在这种地方。对对对，
哦，
就它就比较好做扩充这样子。
那如果我那个就是如果 process B 是从 process A fork 出来的时候，
对，它会复制一份。
对，它复制一份，它这块是用指向同一块，还是它会复制一份出来？
这样它会这样关。
我就指到同一边去。
对对对，这个跟 process 没有关系，它是在系统里面维护的，OS 里面维护的。对，process 有的是这一块，就是 descriptor table。
哦，然后还有，哦，刚才这个说不定跟它这里应该是什么东西？
就是它其实只是一个小分享，就跟大家说，因为你们在用 Windows 的时候可能会用捷径这种东西，就你们右键会产生一个捷径嘛，复制一个档案出来。
啊，
捷径就是 soft link。soft link 的概念就是你今天复制这个档案出来，你如果有2个档案都还健在的话，那你其实不管从哪一个档案去点，它都会给你同样的内容，这样子。就是捷径用途嘛，就你把捷径到别的地方去，它其实都还可以领过去。那它背后的实现就是这样子。但是相较于 soft link，还有另外一个叫 hard link。hard link 的问题就 hard link 的用处就是你 soft link 就是你捷径，如果你把原本档案删了，你捷径就没用了。你如果回去做实验，就是你用 Windows，然后你用一个捷径，你把原本档案直接删掉的话，你捷径那个就会直接无效，他就跟你说你的档案捷径是无效的。
啊，
对，但这个不会，hard link 就是你不管删哪一个，它都会保留，因为它是用 counter 去判断的，就是你接一个 hard link，我就多 counter 多1，所以其实不管是哪一个，它其实都是有权利去连到，就是原本的资料都会有程序权限。
对，可是你刚才不是说把档案删掉，把档案删掉不就这些都没了吗？
对啊，这些都没了，所以这个就爆了。
这个不是也
它不会真的删的，因为它这边会有一个 counter 来去跟后面说你不能删它。删只是对于 process 来讲，它把这个删掉，但是后面的档案要不要删是另外一回事。
所以它可能只是删这个，
没错，
这个路径。
没错，它是删路径而已。
那这个就是实路上有什么举例？
有啊，
像这个就捷径。
例如你现在有2个不同的，这个比较复杂，就是你现在可能2个不同的档案系统，有2个硬碟，那你想备份你的档案，你想让这个档案在2个档案系统都有，对，那你就不需要去什么 copy 资料从一个 copy 到另外一边去，因为你 copy 资料的话，你后面的 inode 就变2个。对，那你现在你用这个 hard link 就是代表你吸收一份资料，但是你现在2边都可以去存取到这份资料，而且并不会因为你的左边的 file system 挂掉，你右边的 file system 就一起挂掉。你左边 file system 挂掉，你右边 file system 还是可以连到这个档案，因为这个档案还是存在的。
哦
它是靠技术去判断的。
哦，
就资料被告的时候比较常用到这种感觉。
比较，所以你应该说删档案是指它删的是接近是
你这个吗？这个意思是你如果删原本档案，你捷径就无效了。当然你删捷径没差，因为捷径本来就是可以删的东西。你删掉捷径，它原本档案还可以继续 access 到。
啊，跟删原本档案不就是删这里的 data 的意思吗？
哦，没有，删原本档案的意思是我把这个东西删掉，但是在这个上面的实作，它就是会把这边一起删掉。
啊，
但是在这个实作不会，下面的哈林实作你删这个掉，它只是把计数器减一而已，然后它的判断会回来去判断说这边的计数器是到0吗？如果没到0的话，就不会把后面的档案真的去把它删掉。
哦，
对，技术可以是指就是前面指向它的
没错，
有几个
有几个这样子，
啊，所以通常我们在电脑上创，然后档案，然后都是这种
你都只能看到这边而已，左半边，后面怎么做你都看不到，就是就算他没有真的删题，你也不知道。
哦，
对，
那哦，就它这个哦，它这个图是怎么？
它这个图其实就是我这样我没有特别直接讲，因为你们还没学到后面的这些有没有什么 D entry 这一些，但这张图其实就是档案系统怎么去管理这些东西。
啊
然后我先跳过这边，我先跟你们讲说，其实，在 disk 上面，它在存的时候就是去存资料结构跟 data 一起存，然后它的资料结构是透过 inode table 去跟大家说你的 inode 到底在什么地方的，这样。然后它的 data 其实分2个部分，一个是 file 的 data，就是你原本的你那个档案是原本 raw data 是长什么样的，它就是存的 file。另外就是 directory，因为你 directory 其实就是存，对于 Linux 来讲，它就是一个 file。那里面就是存它里面的路径的资料这样子，
啊
所以它这个就会有一个叫 directory block，就专门存你的路径这样。啊，不止存路径啊，还会存那个对应关系，就是那个 file name 跟 inode 的对应关系这样。
哦，所以
对
路径，然后再用这个方式找，
对
啊
对
对啊，那这个跟
对啊，
这
这个 inode table 就是存在这里，这就是 inode table。然后这个2个东西啊，process 这个 file descriptor 是你开机之后，你开始跑程式才会出现的东西。
啊，
因为你开始跑程式，你才会开始有程式开档案的问题啊。
对，
所以这个东西是开始跑之后，它会建在机体里面。这个也是，
哦，所以这些哦，
这2个基本上都是在开机之后才会出现的资料结构。
哦
对，因为你 open file table 是用来去建立你的 process 跟资料的这个桥梁。
哦，所以它上面才只会记
对，所以你在硬碟里面基本上只会 inode table。
啊
哎，不是只是啊，只是说我们现在只教到这个，你下礼拜就会，下礼拜就会有更多资料结构在这边出现。对，就像是它这边有什么 D entry 这些啊，下礼拜就会稍微讲一下，这到底是什么意思，到底是怎么回事。
那
对，
好。然后
I think it's better.
哦，它这个应该还可以有很多分支嘛，它这个
对，这只是一个举例而已，它可以到很深。
哦好，那没有了，
好，谢谢。
Last slide.
Sorry，你要签名吗？One moment, let me like make a signature。没问题。好，Sorry。
我觉得
好，谢谢
教授。
谢谢。
I have a question about entry. So each of them will represent.
One moment. Alright.
Yeah. Question on the entry. So each of them will represent a file.
You mean the D entry?
Yeah. Okay. So for example, the OS will read the file location, and
Yeah.
it will read the file, right?
Yeah.
So I am curious about in red configuration. So the file each the values are have like we have two DVRs for the devices and have the data of a file will be stored on each. So it is correct.
You mean each file means you store data in a storage device?
Yeah.
It's correct. Yeah.
Yeah. So how these input entries manage the file. So for example, on the OS level, we see only one file, and how can the data of the file can be mapped and without the OS. So they will use the entries from the board of the device.
I know you actually it just playing around the data structure part. I mean, there's always only one file content in a storage device in most cases. And the reason you can store like different users that can have different, it's just because there is a different data structure maintained by the file system, and they will give you those like illustrations, just like you have the own and unique privilege to access it, just like a virtualization layer. But actually, not only you, all of the users, if they have the privilege to access the file, then they can access. Yeah. For example, I mean, one easier example is just like a hard link. So hard link actually, the raw data, there's only one copy of the raw data. But the hard link is, for example, if you are a user, you have a file called file.txt, and you're going to make a hard link. You can think about hard link just like a copy, but a copy is not for a data part. It's used the data structure to mimic, like you have like extra copies there. And the implementation is they will maintain this kind of hard link data structure, and there is a counter in the inode. The counter can help to identify if how many files they are sharing the same hard link. So in this case, actually, this one and this one, or even some other ones, they are seeing the same file content. So even they are different files, that when you are in the user, you see there are different files. But actually in the store device, there's only one file only. And the reason how it is possible to do this is because there is an inode between them, and then inode can offer the counter. So the counter can say, okay, there is a 2 files or 3 files. So there are 2 or 3 things. So this contents will not be deleted.
Yeah, I mean, is that for example, I mean, I'm going to ask what if the storage is running in RAID configuration? So we have 2 SSD, and one file is store half of the data of its data on one and the other. So the inode entries will point to the data of the file on both SSD at the same time. So there's only one inode entry.
You mean NST?
Yeah. Yeah. One inode entry. So yeah, all there are 2 inode entry for each SSD.
You mean NST? What's the full name for NST?
I mean, like in RAID configuration. So we have 2 SSD.
You mean RAID?
Yeah, RAID.
RAID?
Yeah.
Oh, this is a little bit different because RAID actually is another abstract layer above the file system.
Oh.
So there is a thing called RAID controller, and RAID will maintain this kind of stuff. Yeah.
Okay.
So it is also possible for RAID that there is no file system below. It is also possible to do the thing like this.
Oh.
Yeah. So RAID is a little bit different. RAID is like it is going to control different disk. And for on a disk, you can have different file system. It is possible. Or you don't want to have a file system. You just want to let it as a block device. It is also possible. And for a RAID, actually, you can think about there is also another things very similar to file system, but there's a RAID systems to maintain those kind of stuff.
Wow.
Yep. So they are similar, but they can be used together, or you can use to solve by using the RAID to configure your disk. Yep. And you can also be no file system on it. It is also possible. So a more complex one is you have RAID and you have file system. Yep. But even this, they can still be worked together because they are different layers. Yep.
I see. So it's a structure layer to replace file system.
Yep.
Yeah, I see.
Yep.
Okay.
Okay. Thank you.
Hi, sir. Good afternoon. Regarding the grades for homework 1.
Homework 1, I think you can go to find a TA because homework 1 is graded by the TA.
So I send them an email, but so
Oh,
I'm just waiting for the reply.
If you are going to get a instant reply, you can just directly go to the lab, like 119.
119.
Yeah, just there.
Thank you.
Yeah, thank you.
Bye.
Bye.